we discussed this how to look leveraging locality in memory hierarchy. Now we will many of the techniques we'll discuss. They will use double buffering. So let us explain what is double buffering. So first, let us understand single buffering. Single buffering just means we have a single buffer. So the buffer means temporary storage. That means there will be one producer which writes to the buffer at time t equals to 0. Then after some time, there is consumer. That means whoever needs the data that reads the data from the buffer. So now you can see before because buffer can only have either read or write at a point of time. So producer and consumer cannot work in parallel. If you use single buffering, then producer and consumer cannot work in parallel. Now in double buffering, we overlap the compute and communication by doubling the S1 sizes. So here the point is we use two buffers. So for example, at time t equals to 0, of course, that means even before this time, there was something written in the buffer 0. Okay, something was written in buffer 0. So consumer reads that value from buffer 0 and producer writes the value to buffer 1. Okay, so and then what happens after some time? Now buffer 1 holds the data which the producer just now wrote. Right, so that data is written in buffer 1. And at time t equals to t, small t equals to capital T, that means at certain time capital T. Now consumer can read from buffer 1 and some producer can write to now buffer 0. That means the roles of the buffers are reversed. At one point of time, we were reading from 0 and writing to 1. Now we are reading from 1 and writing to 0. So the roles of buffer 0 and buffer 1, they are reversed. Okay, so producer writes to one buffer and consumer reads from another buffer. In the next cycle, their roles are reversed. So that means both producer and consumer can work simultaneously. Can work in parallel. This is the benefit. Okay, so now we'll discuss clustering, encoding, and factorized multiplication from this author. So whole point is, as we know that FC layers, fully connected layers, they have a lot of weights. So in accessing those weights, these layers become bandwidth bound. So we want to reduce the memory bottleneck. That means we want to reduce the memory accesses. So how do we do that? How do we do that? So we perform clustering, for which we use k-means clustering. Then we use encoding. I will show in 4 slides. So which reduces the data transfer from 32 bits to just few bits. So let us see how do we first. I will show clustering and then we'll show encoding. So the idea is clustering, encoding, and factorized multiplication. We have 3 techniques. We have 3 techniques here: clustering, encoding, and factorized multiplication. So first of all, suppose we have 4 cross 4 matrix where we have total 16 elements. Okay, now these are FP values. Each FP value, suppose single precision, that means each of them is 32 bits. Then we use, suppose k-means clustering, where we use k equals to 2. That means we use 2 centroids. So we found out 2 centroids, 0.8 and -0.7. So that means most of the, some of the values will be close to 0.8 and other values will be close to -0.7. So we replace original values with their centroids. Matrix values replaced by centroids. So this is called clustering. That means, see, there is some approximation involved. Right? This is the approximate computing, but approximation is tolerable, within tolerable range. So we replaced 1.3 by 0.8. We replaced -0.2 with -0.7. Okay, so now, as you can see, how many distinct values are there? Can anybody tell me how many distinct values are there now? Anybody can tell me how many distinct values are there in the matrix now?
Sir, 2.
2, yeah. There are only 2 distinct values, either 0.8 or -0.7. So first of all, instead of 16 values, now we just have 2 distinct values. Okay, so and now even for those 2 values, instead of storing the exact value, we can just store the index, or you can call it encoding. So here 0, we are encoding 0 to represent 0.8 and 1 to represent minus 0.7. Okay. That means whenever it is 1, it is not 1, it is minus 1.7. So that is encoding, right? Encoding means we, instead of one thing we write another symbol. Instead of one symbol, we write another symbol, which is expected to be shorter. So that is encoding. So we, instead of 0.8, we wrote 0, and instead of minus 0.7, we wrote 1. So two of the techniques we have already implemented. So clustering and encoding. And what we said, we use encoding of parameters, which reduces the data transfer from 32 bits to just few bits. So here, instead of fetching this 32-bit data, now we just need to fetch 1-bit data, because that 1 bit can be either 0 or 1. So that's the data we fetch. Okay, so that's the idea. Now this NVM means matrix vector multiplication. So now we'll do factorized multiplication. So now how do we optimize the multiplication? So now we will perform factorized multiplication of uncoded values, which will reduce the number of multiplications at the cost of probably, it's not necessary that number of additions will increase, but probably number of additions will increase. So let us see how. So this is our original idea, that if suppose we had these weights and these were the inputs, we will multiply them. So 4 multiplications and 3 additions, right? We will add this with this with, this with this, and this with this. So if we add one after another, we will have three additions. Or if we have like one, we add this in this and this in this in parallel, and then we add their sum. So again, 3 additions. So 4 multiplication and 3 additions. Everybody agrees with this? This is the traditional case. Now, here with the encoding, what we do, we don't multiply first. We first take the common factors out, right? So here, for example, this number 0.3 and this, they are getting multiplied with the same value. Right? They are getting multiplied with the same value. All of them are getting multiplied with 0.8. So we first of all add them. So 0.3 is added with this, and this is added with this. So till now, how many additions? 2 additions. This with this, and this with this. So 2 additions here. Right? Now we multiply this with this. Sorry. This and this. When you add it, it becomes. When you add 0.3 with 0.6, it becomes 0.9. 0.9 minus 0.5, so it becomes 0.4. So we have 0.4 and 0.9. And if we multiply them with original numbers, 0.8 and minus 0.7, it becomes the same answer. So the result is same. But now we have to do just one more addition here. So 2 plus 3, 1 addition here. So that means total 3 additions and only 2 multiplications. Okay, so 2 multiplications and 3 additions. So now we have reduced the number of multiplication by doing this factorization. And this factorization is like probably you must have read it in your 8th standard or 7th standard. So in this way, we have what all we have done. We have reduced the number of memory accesses, and we have also reduced the number of computations. Both optimizations. So if you remember our main presentation, we had discussed compute-related optimization, memory-related optimizations. So this technique does both the optimizations. Factorized multiplication, right? And by using this clustering. So clustering, we have done both clustering for weight sharing and factorized multiplication to reduce the compute. So in the same technique, they have proposed both. So anybody has any question?